In this lecture, we're going to do something that's very exciting, very fun, and we're going to compute homology using the Vietoris sequence. So we're going to compute homology by the Vietoris sequence. There are other methods for computing homology. We actually talked about previously using triangulations. But the issue, of course, with triangulations is that sometimes when you triangulate spaces, they might become fairly complicated as there's quite a number of triangles, and it especially becomes more complex as the dimension grows. And then trying to keep track of how all of the triangles fit together might become confusing at a certain point. So it is a nice approach, but it is, of course, not the perfect approach. So there's other approaches, and the Vietoris sequence is another approach. But it's not, just like any other approach, it's not the perfect approach. It will not work for every example you can imagine. There's other methods as well, but it's at least something. And that's what we're going to discuss. And this is actually reminiscent. So if you happen to be familiar, so if you know the Seifert-von Kampen theorem, this approach, the Vietoris approach, is similar. You can actually call it the analog of the Seifert-von Kampen theorem. Now, if you do not know the Seifert-von Kampen theorem, that is okay. That's fine. You can still follow along. It's just a nice analogy. In the Seifert-von Kampen theorem, the idea is that you take your space and you decompose it as a union of two open sets. And then if you know the fundamental group of U, V, and their intersection, then you can find the fundamental group of the space itself. It's not that easy, but that's the basic idea behind it. You're reducing the problem into two smaller subsets on which you can solve the problem. Now, with the Seifert-von Kampen theorem, there is an assumption that these are all path connected. But in the Vietoris sequence, we do not need that whatsoever. In fact, in the Vietoris sequence, these do not even have to be open sets. So if you want to see a generalization of this, you can look in the Breton book, and he generalizes it to arbitrary sets, but the requirement is that the interiors of the set cover X. But we're not going to go there. This is going to be good enough for us. Now, the Seifert-von Kampen theorem is specifically for pi 1. But when we use the Vietoris sequence, we will be able to calculate this not just for H1, but for any H, so for Hn. So if you know the nth homology of the two individual open sets and how they intersect, then you can piece that information together. You can glue it together to recover the homology of X. So let's do a quick review of the Vietoris sequence. So we're going to assume that X has been written as a union of two open sets. Then the following sequence is exact. So exact means that the image of every incoming map is exactly equal to the kernel of the outgoing map. So this is Vietoris sequence. So let's start at Hn. So Hn of X. Then you have the lowering of dimension map, Hn minus 1, into the intersection. And then before that, you have Hn of U plus Hn of V. And then before that, you have Hn of U intersect V. And then before that, you have Hn plus 1 of X, and so on. So there's three types of mappings. These are going to be homomorphisms. So there's three types of mappings. You have a mapping from the intersection to the sum. Then you have a mapping from the sum to the space, to the total space. And then you have the lowering of dimension mapping. That's the trickiest one to describe. All of these mappings are sort of the obvious mapping. So let's just quickly go over how this works. The way this one works is if you have a cycle, an n cycle, so a homology class of an n cycle in the intersection, you just map it diagonally. So it's just the cycle itself and the cycle itself. And of course, these brackets are, of course, understood that this is the homology class in U, and that's the homology class in V. So in particular, this is not necessarily injective, because it is possible that in the larger space, because you have more space to move around, it is possible that the cycle becomes homologically trivial. So just be careful. It looks like it's an injection. It's not actually an injection. I mean, it could be an injection, but it does not have to be an injection. The next mapping that we have, it's the mapping from the sum to the total space. The way this one works is that if you have, let's say, C1, and then you have C2, so C1 here, it's a representative in the homology class in U, and C2 is a representative in the homology class of V, then the way you map it into X would just be you take the sum, I'm sorry, not the sum, you take the difference of the two cycles. This is the homology class in X, and that's the homology class also in X, because these are both subsets of X. And we make the arbitrary choice that we subtract from the first one, we subtract the second one. You can also do it the other way around. But depending on the choice that you make, the mapping, the lowering of dimension map, it will reflect that choice in order to keep the sequence exact. So the trickiest one is to describe how that one works. That's the trickiest one, but it's not too bad. And the way it works is you pick a homology class in X, and then you can write that homology class as a sum of two chains, A and B, where A is an n-chain whose image is contained in U, and B is an n-chain whose image is contained in V. So writing, decomposing a cycle in such a way, this is what we call barycentric subdivision. It's a very technical lemma in homology, but the idea is very simple, that if you have two overlapping open sets, well, they do not have to be overlapping, but in general, if they're overlapping and you have some kind of simplex, then you can take that simplex and cut it up into small little pieces so that the chains that make up the simplex are entirely contained in U or V. So the cycle is a sum of simplices where each one sits in U or V. Now, we want to be careful. We're not saying that C is equal to A plus B. We're not saying that. But because we're using homology, you can say the homology class of C becomes homologically equivalent to the sum of those two. So you can replace the homology class by this. And also, we're not saying that A and B are cycles themselves. That's the reason why we're not saying that this is A plus B, because that would not make sense. A and B themselves do not have to be cycles. They're just chains. In general, they're just going to be chains. Together, they give you a cycle, but individually, they're going to be chains. And the way this lowering of dimension map is defined is you take the cycle that is in U, and then you apply to it A. And then you take the homology of that, the homology class of that in the intersection. You see, the choice is arbitrary. You could do it with B, but the reason why you're doing it this way is because the map that's going from the sum into X, you're making the arbitrary choice to take this with a positive and to take that one with a negative. If you do it the other way around, then you have to use the negative sign, because the boundary of C would be homologically equivalent to the homology of A plus B, but the homology of C is 0, and so you get the boundary of A plus the boundary of B, and so you're saying that the boundary of B is homologically equivalent to negative the boundary of A. So if you choose to use the other one, then you have to choose it with a negative sign. And this is in order to ensure that this sequence of groups is exact, that the image of the incoming map, it coincides with the way this one is being constructed. So this is how these morphisms are defined. And as we remarked, the sequence is exact. We gave a partial proof of that. It's otherwise very tedious to prove it is exact, but it has to do with that zigzag sequence and all of that. So this sequence is exact. That's how the maps are defined. Often, maybe I should say this, often when using the Vietoris sequence, it is not even necessary to figure out these mappings. Sometimes the exactness alone is sufficient to compute homology. Not always. In some examples which are more complicated, you actually have to think about those mappings in more detail. But basically, if you're wondering how do you know if you have to actually exploit the mappings to compute homology, well, it's just an issue of necessity. Sometimes when you're using the Vietoris sequence, you realize that you're not able to come to a conclusion from just the exactness of the sequence, and you have to do something else. If it's not clear what I'm saying right now, it will become clearer as we look at some of the examples. So now I would like to move to some of the examples, and this will help clarify how you use this method of homological calculation. For our first example, without any surprise, we're going to start with the homology of the circle. Perhaps the simplest space that has non-trivial homology. And we already know many different methods for computing homology of the circle. So the circle, of course, can be triangulated, and then you can use simplicial homology. You can do it like that. Another thing you can do is you can calculate the fundamental group of the circle and then apply the Horevich isomorphism. And since the fundamental group of the circle is already abelian, it is the group of integers, its abelianization is the integers again. So the first homology of the circle are the integers. But the problem is the Horevich isomorphism does not tell you anything about H2 of the circle. So we still have to calculate H2 of the circle. However, if you triangulate the circle, then the triangulations will determine the homology of all dimensions. So we already know how to do it, but I specifically want to show you how to do it with the Vietoris sequence, because for learning purposes, you always want to start with a nice, simple example that nicely illustrates everything. So we're going to use a fact here. So this is sort of like a fact that we alluded to before, but I want to make it explicit, that if X is homotopic to Y as two topological spaces, then their fundamental groups will be isomorphic, because homology is a homotopy invariant. The way you can prove this fact is very simple. You're going to let F be a map from X to Y, G map be a map from Y to X, so that when you do this composition, you get something that's homotopic to the identity on Y, and when you do this composition, you get something that's homotopic to the identity on X. And then you apply the fundamental group functor. So if you apply the fundamental group functor on this, you get F star is an isomorphism from Hn of X to Hn of Y. And when you do it the other way around, you get G star is a map from the homology of Y into the homology of X. And we know that if we compose them together, if you do F star composed with G star, that's the same thing as F composed G star. Why? Because the induced because the homology group functor, I'm sorry, the homology is a functor. So the induced isomorphism of a composition is the induced isomorphism of the comp. So in other words, if you take a composition of the induced, the composition of the induced homomorphisms is the induced homomorphism of the composition. This is just the fact that the homology functor respects commutative diagrams, right? That's basically what we're saying. And because F composed G is homotopic to the identity, this is just the identity Y star, which is just the identity, right? We proved that maps that are homotopic, two maps that are homotopic, the induced maps on the level of homology are equal. So that's just the identity. This is the identity on the group, and then you can do it the other way around. And so what you see is that these become isomorphisms. So that's just a very sloppy, quick proof of something we've seen before, but we're going to use this fact. I'm just going to remove it. Just a quick reminder in case you're bothered by this fact and how one would show it. But now let's get back to the homology of the circle. So we know that the homology of the circle is, the zero homology of the circle is isomorphic to Z, because H0, this is basically the number of path components. This is something that you had on the homework. It counts the number of path components. Since the circle, so this is a 0 and that's a circle. Since the circle, maybe I should just write S1 to avoid confusion. Since the circle is path connected, its zeroth homology would just be isomorphic to Z because you only have one path component. So the zero homology, there's not much to say about it. What we're going to do is we're going to compute H1, and H2. We're not going to compute H3 because when you reach H3 and beyond, it sort of becomes a little bit too trivial. It's not very interesting. You will actually have a problem on the homework for computing homology of spheres, and you'll get to play around with this. So let's start with the first homology of the circle. And what's going to be interesting is, so interestingly, H1 is harder to compute than H2 in this example. In other examples, it might be different. So let's start calculating H1. So to use the Vietoris sequence, we have to decompose our space as, so we're going to have a U, so this is going to be, so this is S1, this is going to be U, it's going to be like the diameter and something a little bit beyond it, and then this is going to be V, two circles that do not close up, and then when you intersect them, you get these two pieces, like that. By the way, I should say that all of these computations can be made rigorous, but that is what we call missing the point. In order to make them rigorous, every one of these computations has to be a lot longer. So a 15-minute computation where you sort of draw pictures and you illustrate carefully the main ideas that are being used, if you were to supply a carefully written proof for every little claim that you're making, it will turn into like a 1-hour computation. The point of these calculations is to give you the intuition, to give you the idea of how the computations are being done. And then if you are mathematically mature enough, you can fill in those details yourself, the ones that require small justifications along the way. Okay, so now here's what we do next. So we write it like this. Now I should say the idea is U is a contractible space. It collapses to a point. V is also a contractible space. It collapses to a point. And U intersect V, it collapses to two disjoint points because you have two components here. So we know the homology of these three, and we need to find the homology of S1. And this is the perfect setup to use the Vietoris sequence. So we're interested in the first homology of S1. So according to the Vietoris sequence, there's a lowering of dimension map into H0 of U intersect V. And there's a lowering of, and then there's a map into H0 of U plus H0 of V. And then here we have, on the other side of the sequence, we have H1 of U plus H1 of V. And then here we have H1 of U intersect V. So this is the sequence. So this is the relevant part of the sequence that we're going to be using, because this is the part of the Vietoris sequence that contains the homology of S1, the first homology group of S1. So now let's begin calculating what these groups are. So H0 is the number of components. So you have two components. Actually, I just want to do a very quick recap. Let me just move this out of the way. This is a quick recap. So Y is H0, the number of path components. I think this would be very helpful to think about. So here's what it has to do with. Let's say you have a path connected space, and you pick a point P, and you pick another point Q. Then H0 of X, these are going to be 0 cycles in X. But a 0 cycle, it's just a point. So this is the group that's generated by points. But you have to realize that if P and Q are in X, then P is homotopically equivalent to Q. Why is that? Well, because if it's path connected, there is a path from P to Q. So if you call that path F, then the boundary of F would be Q minus P. So you can see that the difference of 2 points can be expressed as a boundary of a 1-simplex. So therefore, different points are equivalent if they can be connected by a path. However, if your space has two path components, okay, so you have, let's say, a point over here, and you have a point over there, then you cannot find a path that contains them. And then what's going to happen is the 0th homology of X, it would be then isomorphic to 2 copies of Z. And if you want to write it more appropriately, you would say it's the homology class of P, because any point in this component will automatically be homologically equivalent to P, and you're just including the multiplicity here. And anything in this component would be homologically equivalent to Q. And then you're just including a multiplicity there. So the group would therefore be generated by these two classes, and then you just consider arbitrary multiplicities of those two, and that's why you're getting that the H0 group is isomorphic to a direct sum of two copies of Z. So it's the number of path components. So we're going to be using this fact as we do this with the circle. So this is just going to be helpful for us. So I'll kind of put it over here again. So this is our example with the circle. So now let's do this. So H0 of the intersection, this is going to therefore be isomorphic to Z plus Z. And the way you get, it's what we were saying, you pick a point in each component. So you pick a point P, and you pick a point Q, and those 2 points are in each component. So if you really want to write it out maybe more explicitly, you would say that this is the group of NP plus MQ, where N and M range over the integers. And here, P and Q are going to be different. These are non-homologous to each other, so these are different classes. So that's why you have it over here. But something interesting happens in this one. So this group, now H0 of U, it only has one component. So this is going to be Z plus Z. This one is also a single component. But how is the map defined? So in general, I'll write it down here. So in general, the map takes a class, a homology class, and it maps that homology class to just basically its diagonal. You sort of repeat it twice. That's what you're sort of repeating it twice. So that's what this map does in the Meyer-Vietoris sequence. It's what we call the diagonal map. You just repeat the class twice in each of the two open sets. So you're going to take this class, this cycle, and you're just going to repeat it twice in each one. So this is going to be, therefore, be a pair NP plus MQ, and then you have NP plus MQ, like this. So you just repeat it twice. But now here's the part which makes this quite interesting. You need to understand that the class of P and the class of Q are different in the intersection, because the intersection is not path connected. But in U, the points P and Q, they're part of the same component. And since they're part of the same component, that means Q is homologically equivalent to P. And likewise, the same thing happens in V. So that means that this NQ can be replaced by just P, and this can be replaced by just P. Or you can replace it if you want by Q. It does not really matter. But in the end, what we're getting is that this is just N plus M P, N plus M P. That's what we're getting. So you're just adding these two coordinates together, right? Those two coefficients together, I should say. And so the mapping from this group to this group, it basically does this. So in more simple notation, you're taking a pair of integers and you're mapping those pair of integers to the sum, and you're just repeating it twice. So that's what the map is doing. So I'm going to remove this so it does not get in the way, but this is really the map. And actually, let's fill this in. So U intersect V, it's 2 points. Well, we need a lemma here that we never, so I guess I should write a lemma. It's very simple. What is the nth homology of a single point? So it's Z if the dimension is 0, and it's 0 if the dimension is positive. This should seem obvious, and it's not difficult to prove. But this is the homology of a one-point space. So now let's return back to our example. U intersect V, this is a contractible space, right? These contract down to a point. So this is the homology of a two-point space. And so its first homology is 0. So this one is just going to be 0. And this one, H1 of U, well, U is contractible and V is contractible. So these homologies are 0 again. Okay, so I think what I should do is, so let me do this. I'm going to remove, this is going to get in the way. So let's give some names. Let's say this arrow, I do not think we need this one. So I think this is unnecessary. I think I only need this part of the sequence. So let's call this one F. That's the name of the map. Let's call this map G. And let's call that mapping H. Okay, so let's focus on the one in the middle. So G is a map from H1 to S1 to H0, U intersect V. So it would mean, so this is just a well-known fact from algebra, that when you have a homomorphism between two groups, that the image of the homomorphism is isomorphic to H1 of S1 mod the kernel of G. Right? This is just the, I guess they call this the fundamental isomorphism theorem, right? Something along those names. You use this a lot in algebra. Right? The image of a homomorphism is isomorphic to the domain modded out by its kernel. But now we're going to use exactness of the sequence. So the kernel of G, that's the kernel of the outgoing map, that's equal to the image of the incoming map. So this is the image of the incoming map. So that's the image of F. But F, this is the 0 map, because this is the 0 group. So that's just the 0 map. So you're modding out by 0. Right? So you're just modding out, this is just 0. You're modding out by 0. So you're just, in the end, you're just getting something that's isomorphic to H1 of S. And so what we see is that the fundamental group, I'm sorry, not the fundamental group, the first homology group of the circle is isomorphic to the image of G. It's the image of this map. But we're going to use exactness again. The image of this map, the image of G, is going to be the kernel of H. So now let's find the kernel of H. So how do we find the kernel? Well, the kernel of H, notice what H it's doing. It's taking a pair of integers and it maps a pair of integers to their sum repeated twice. So how do you end up getting 0? So that would be the kernel. So if it gets mapped to 0, 0, 0, then the only way this happens is that if the second coordinate is the negative of the first coordinate. So the kernel would then consist of all numbers of the form n comma negative n, where n is an integer. But that's just another way of saying that that's isomorphic to the group of integers, because the second coordinate is determined by the first. So in the end, it's just the group of integers. So we have proven, so thus, the first homology of the circle is isomorphic to the integers. And this gives us another way to get the homology of the circle. Now, we can actually do a little bit better. Yeah, so here's what we can do. So let me remove this. So we can ask this question. So as a follow-up question, we can ask what one cycle in the circle in S1 generates the homology group? I mean, that's a reasonable question to ask, because if it's isomorphic to the integers, that means there's a generating cycle. There's one generating cycle for the whole group. So what is that cycle? So we'll do it in this example. A lot of the times when you're computing homology, sometimes that's not even necessary to know. Like if you know that something is isomorphic to, let's say, 3 copies of Z, then there's going to be like 3 different types of cycles that generate the homology group. But sometimes it's not even necessary to know what those are. But I think it's just a nice example to just work this out. So let's remove all of this and see how to do it. So we've established that it's isomorphic to the integers. So what do we do next? Well, so yeah, this is the one that's isomorphic to the integers. So let's kind of remove this. And understand. Okay, so this is the one, so the image of G, right? So the image of G, as we said, it's the group that, I mean, it's the following subgroup, n comma negative n, where n is an integer. So now what's the generator for this group? So image of G is isomorphic, of course, to Z with generator 1 comma negative 1. So what we want to do is, so we want to find a one cycle in this homology group which maps to 1 comma negative 1, right? Because because we've said, well, so maybe say it again. H1 of S1 is isomorphic. It's isomorphic to Z, right? It's isomorphic to Z. More specifically, G, the image of it in the subgroup, it's isomorphic to G, and the generator, it's really isomorphic to this, we should say. And that's the generator. So because you have this isomorphism, there has to be a generating cycle that gets mapped to the generator 1 comma 0. And the question is, what is that generating cycle? So here's the way we do it. This nicely illustrates this idea of the lowering of dimension map from H1 to H0. So here's how it works. You're also going to see how barycentric subdivision is going to be used here. So basically, let's go back to our circle again. And for the cycle, let's take the cycle that wraps one time around. It does not matter where it starts, but let's take a cycle that wraps one time around the circle, like this. So we're going to call that C. And we claim that the class of C generates the homology group for the circle. Okay, so what do we need to check? So we need to check, so let's remove this G over here. We need to check, in fact, let me remove all of this. This is just going to get in the way. So what we basically need to do is we need to show that this cycle, it gets mapped to 1 comma negative 1. It gets mapped to the generator in this group. And this is the lowering of dimension map that comes from barycentric subdivision. So let's see that it actually works. This C can be decomposed into two pieces. So the C that goes around, it can be decomposed into two pieces. One of them, which we can call A, the one that goes, the lower one, and one of them that goes above it, which we call B, like that. So we can say that the homology class of C can be represented as A plus B. So I'm not saying that A plus B is equal to C, because this is a list of two mappings, and this is a single mapping. So, but when we work with homology groups, we're talking about homology classes. So the class of C will be homologically equivalent to these two. So C can be replaced as D. Now these are chains, these are not cycles anymore. But the way this lowering of dimension works is you're going to take the one, you see the A, the one that goes like this. So you have to take the one that sits inside U. So U is the one that goes first. So you're going to have to take the B one. Yeah, you're going to have to take, you're going to write it like this, B plus A. And then you're going to, this mapping is going to take C and it's going to map it to the boundary of B. It's the one that sits inside U, right? This is the one that sits inside U. And how do you find the boundary of B? Well, it's that point minus that point. So it'll be Q minus P. And the 1 is referring to the P. So this is actually negative 1, 1, right? Because if you recall how we were getting those two numbers, the first one was the class. Oh, sorry about that. Yeah, so Q minus P, that's right over here in the intersection. So the first coordinate represented to how many copies of P you use, and the second coordinate was showing the multiplicity of Q. So actually we're getting minus 1, 1. But it's not a big deal because this is also a generator, right? That's also a generator. If something is a generator, its negative is a generator. So, so the point is, this cycle that goes around one time, that winds around one time around the circle, because you can decompose it in such a way, we see that the lowering of dimension homomorphism, it takes it into the generator for that, into the group that it's isomorphic to. So we found the generator for the homology of the circle. So now let's find the second homology of the circle, and this will actually be easier. So let's clear this away and start again. It's going to be the same setup as before. We have the circle, we have U, let's say this is U, we have V, and then we have their intersection. And I'm going to find the second homology of the circle. So we have the lowering of dimension map, U intersect V, and then we have H1 of U plus H1 of V. And now, well, and I think that's going to be it. I do not think we need anything else. Well, let's see. I'm not sure. So this one, we said this is going to be 0, and this one we said was going to be 0. And let's call this one F, and let's call this one G. So we basically have a situation where you have 0 going into F, you have a mysterious group in the middle, and then you have 0. So the question is, can we say anything about the mysterious group in the middle? Does it have to be 0 itself? So let's see. The image. Okay, so I think that would actually do it for us, because the image of F is equal to the kernel of G. It's exact right over there. But the image of F is going to be 0, because you're just mapping as a 0 group. So the kernel is going to be 0. So that means that this is an injection into 0. So you're saying that H2 of S1, it injects into 0. Well, the only way that can happen if this is the 0 group already. So this has to be the trivial group. So you can see this was very easy to show that. In fact, this example illustrates that we do not need to understand how the maps operate. The exactness of the sequence is sufficient here. This is in contrast to the previous example where we had to understand one of the maps. Like, basically, we had a situation where we were mapping 2 copies of Z to 2 copies of Z, and we had to understand what that map was doing to do the calculation. Here, it's not even necessary. It's even easier in this case. And here we have a theorem on homology. And I'm just going to put this on the homework. You'll be able to do this yourself. That the nth homology of the M sphere, so we're going to assume that this is a non-degenerate sphere. So M is at least 1. This is going to be isomorphic to Z if N and M are equal. Is going to be Z if N is 0. And it's going to be 0 if otherwise. So for instance, H3 of S2 would be 0, but H2 of S2 would be Z. H2 or H2 of S3 would be 0, H1 of S3 would be 0, but H3 of S3 would be Z. So that's what it says. So when you have a sphere, the only non-trivial homology that you get is in dimension 0, which is the number of components, and when the homology dimension matches the sphere dimension. This is not difficult to show. It's actually very similar to what we did with the one-dimensional sphere. So I think it would be better to just put that on the homework and you think about that. So now we'll move to the next example. For this next example, we're going to calculate the homology of the projective plane. Homology of P2. And we're just going to find the first homology and the second homology. The 0 homology is rather trivial because the projective plane is path connected, so we know what that's going to be. The higher homology groups are going to be 0. You do have to really show that, and you will be able to show that, but I just want to focus on the first and second homology groups, which are going to be a lot more interesting. So first, how do we think of the projective plane? So the projective plane is defined to be as the sphere modded out by the group of automorphisms, where the group of automorphisms is the identity and the antipodal map. So this is what we're going to do. We're going to draw a sphere, and then we understand that the upper hemisphere, it gets identified with the lower hemisphere using the antipodal map. So they get glued together in this antipodal sort of a way. Now, to use the Vietoris sequence, we're going to write P2 as a union of two open sets, and this is the way we're going to do it. U is going to represent this upper cap right over here, and V is going to represent the other side of the upper cap. But you do have to make V a little bit thicker to make sure that they overlap, because if they do not overlap, then the union will not give you all of P2. These are, after all, open sets, so there has to be a little bit of separation. I'm sorry, because they're open sets, the only way you can get P2 is if the other one goes a little bit above it. So the V will have to be a little bit bigger. But I'm going to draw it in a separate picture so it's easier to see. So V is going to be this one, so it's a little bit higher up, but it's the other side of this, like this. And you will notice I'm not filling in the lower part of the sphere, because the lower part of the sphere is being repeated anyway. You only have to focus on what happens in the upper hemisphere because of this equivalence. So this is going to be V. And when you intersect them, so when you do U intersect V, you're basically going to get this collar going around the sphere, like this collar. So this is going to be U intersect V. And we're actually going to find, so let us first find the homology, the second homology of P2. Because it's easier, and it's going to help us find the first homology. So we go to the Vietoris sequence. So we have this. Here we have H2 of U plus H2 of V. These are going to be 0 because U, well, U is contractible to a point. V, well, actually, V is, so this is the tricky one. U intersect V, this is contractible, well, not contractible, this is homotopic to the circle, because you can sort of like homotope this collar or a cylinder down to a circle, right? You basically just have a cylinder over here. You have a cylinder, and you can just imagine that you just homotope it down onto its inner ring. So the intersection homotopes to a circle, U homotopes to a point. Now the tricky one is, what about this V over here? So, well, how do you even visualize what V is? So basically what V is you want to imagine a cylinder, and then the points on the boundary of the cylinder, yeah, the points on the boundary of the cylinder, they're being glued with the points that are antipodal. So it's not clear exactly what you get. But fortunately, you do not even need to know what you get. It should be, I mean, you can basically do this. You can take a homotopy, right? You can just imagine bringing down all of those lines until you end up on this diameter, but then the diameter is being sort of repeated twice. So you're getting a circle, right? You're getting this arc, but the arc is being repeated again. So you basically just get a circle. So this is also homotopic to a circle. This is homotopic to S1. Okay, so, and now we can say what H2 of U is. So H2 of U, well, that's the homology of a single point. That's trivial. And H2 of V, that's the second homology of S1, which is also trivial. Actually, the previous example with the circle is useful here. So this is just going to be 0. Now, you have H2 of P2 going into, now you have the lowering of dimension map. This is going to go to H1 of U intersect V. And then this is going to go into H1 of U plus H1 of V. Now, H1 of U, that's the one that's easy to understand, because that's just a point. So its first homology is just going to be trivial. Whereas H1 of V, that's homotopic to a circle, so its homology will be isomorphic to the integers. So here, you're getting the integers. And here, well, H1 of U intersect, you're getting the circle, right? You're getting the circle. So that's the homology of the circle. So, right, so that will be the homology of the circle. So this is just Z again. And let's call this map over here. Let's call this map F. And let's call this map G. FG. This map is clearly 0. So we have this exact sequence, and now here we actually need to understand what G is. So what exactly is G doing as a map from the integers to themselves? It's tempting to say that an integer is being mapped to itself, but that would actually be incorrect. If you want to be a little bit more specific, just to be a little bit more careful. So this is basically what we're saying. We're saying that this group is isomorphic to Z. This group is isomorphic to Z. And we're replacing these two groups by just copies of Z. And you want to be able to say what is the corresponding map that will make this diagram commute. So we're basically translating the morphism between homology group into the language of just integer mappings. That's basically what we're trying to do. So the notation is easier. But this is the part which is tricky, because at first, you would say that you're just mapping an integer to itself. But this is actually incorrect. So here's the way we're going to figure this out. So it is isomorphic to the integers. So let's find the generating cycle. So the generating cycle for a circle, so I'm sorry, over here we have a circle. So the generating cycle for the circle, it's the one that goes around one time. So it's the one that winds around one time. So in the picture, this is going to be the cycle that goes around one time. Let's call this one C. Now, let's figure out what's happening here. The first factor, this is just trivial, so it does not really do anything. It's the second factor that we're going to focus on. It's isomorphic to Z. And we saw that V is homotopic to the circle. So we have to find the generating cycle. The generating cycle for the circle, it's the one that winds around one time. So in our picture, now you have to understand that when you homotope V, you homotope it down to this boundary. And because this is a projective plane, the arc, well, the equator that's facing you is identified with the equator that's going back. So the equator that's facing you, its endpoints get glued together. So as you travel along the equator that you see, you're actually traveling across, it's going to give you a cycle. So this over here is going to give you a cycle, and let's call that cycle A. It's the one that winds one time around the circle, right? This is the one that winds one time around the circle. So the generator class for this homology group, it's we'll write it over here. This is just a class of C. And the generator, so when you map, yeah, so you have to, so maybe we'll just say it over here. The generator is C, and here, the generator is A. Okay? Now, here's what you're doing. G, it is taking this class, this generator class, and it is mapping it to itself. So at first, it looks like it's the identity because C goes to C. But you have to be careful. The notation is deceptive. This is the homology in the intersection, whereas this is the homology class in V. So you have to express this one in terms of A. And actually, expressed in terms of the generator, this is 2A. Why is that? Well, here's the reason why. Because notice that in C, you're going around this cylinder once. But as you bring it down towards the equator, you see, as you bring it down towards the equator, the C, it winds around this equator, and then it winds around the equator again. So it really transverses twice around it. So the analogy so the picture that I like to draw is, let's say we have a Mobius band. I think this really makes it a lot nicer to see. So let's say you have a Mobius band. Yes, something like this. So you have a Mobius band. Now the Mobius band has the center line that goes around it. Okay? So the homology of the Mobius band, let's call it M, is isomorphic to Z, because the Mobius band it's homotopic to its center line. And the center line, this cycle, is the cycle that will generate the fundamental group. Now, look what happens when you go along the boundary of the Mobius band. When you go around the boundary of the Mobius band, like this, you actually, I guess I should kind of keep on going it from the back, you actually travel, as you can see, you wind around twice. You wind around twice this one. So if you go around the boundary of the Mobius band, that's not actually the generator for the class, right? The generator class for the homology group. You're actually going around twice. So this is sort of similar to what's happening over here, that V homotopes to this equator, and these points get identified. So when you travel along A, like from that point to that point, you're doing one complete revolution. Here you're doing one complete revolution on V, but this blue path homotopes to and as you homotope it, as you move it down, right? So as you move down the C, right, you kind of keep on sliding down C until you homotope it down to the equator. And as you move it down to the equator, suddenly you're moving around twice. So in terms of the generator class, right, because you're trying to understand this map in terms of generators, so the generator here gets mapped twice to generator over there. So really, this mapping is not the identity mapping, it's the doubling map. It's the map that doubles, right? It maps an integer to twice the integer. So this is the mapping over here. So with this picture, well, with this exact sequence, we can now compute the homology of P2. So maybe what I can do is I can say that maybe, yeah, so here's the way that it goes. The kernel, the image, you know what I need? I need another map. So let me call this map H. So let's call this map H. So we have H2 of P2 being mapped into Z, right? This is Z. And we're going to say that H2 P2 mod the kernel, this is the fundamental isomorphism theorem, is isomorphic to the image of F. Now, the kernel of F, right? The kernel of F can be replaced by the image of H. So H2 of P2, you can just replace this by the image of H, which is just 0, right? So you're just getting H2 of P2, which is isomorphic to the image of F. But the image of F is equal to, right, the image of F, that's equal to the kernel of G. That's equal to the kernel of G. But the kernel of G, this is the mapping G. This is the doubling map. And the doubling map is injective, so its kernel is going to be trivial. So this is just 0. And look at what we've proven. We have proven that the second homology of the projective plane is actually the trivial group. That's what we've proven. So now let's calculate the first homology of P2. It'll be the same kind of pictures, but we'll have a different kind of a sequence because we want to focus at a different part of the sequence to do this. So let's remove all of this and let's start the calculation again. So what we'll do here is we want to work with the first homology of P2. This is going to be mapped into, this is the reduction of dimension. This is U intersect V. This one is going to go into H0 of U plus H0 of V. This one is going to be H1 of V plus H1 of U. And then there's one more, which is H1 of U intersect V. So now let's fill in what we know. So we've said that this one is isomorphic to Z, and we said this one is isomorphic to Z. And the corresponding map here is really the doubling map. So that's actually coming from our previous work. H0 of U intersect V, well, you can see in the picture that this is path connected. So this one is just going to be Z. And this one is just going to be, well, these are, U and V themselves are path connected. So that'll just be two additional copies of Z. And now let's give these mappings names. So let's call this mapping, so for lack of a better name, let's call this one alpha, let's call this one beta, gamma, and delta. And now we're going to use this information to help calculate the homology. So let's focus on this map gamma. So we have a map gamma from H1 of P2 into Z. So by the fundamental isomorphism theorem, this mod out by the kernel of gamma is going to be isomorphic to the image of gamma. Actually, I do not think I want this. Sorry about that. I want to focus on the map beta. So sorry about that. I want to focus on beta. So beta, this is a map from Z into H1 of P2. And so Z mod the kernel of beta is going to be isomorphic to the image of beta. Okay, now because the sequence is exact, so let's talk about the image of beta. So the image of beta is the kernel of gamma. So let me look at this again. So I'm focusing on this map beta that takes us from Z into the first homology group of P2. So by the first isomorphism theorem, if you look at the kernel of beta, that's going to be isomorphic to the image of beta. And the image of beta is the kernel of gamma. Okay, that is correct. Okay, so now let's look at this map over here, delta. Delta is an injective map, because this is the mapping that simply sends an integer to its diagonal. So I leave that for you to think about. This is actually very simple because this is the H0 homology. So that's just determined by path component. So this is actually very easy to understand. So this is an injective map. Okay, this is an injective map. So that means that the kernel of delta is equal to 0 because it's an injective map. But then by exactness, it means that the image of gamma is equal to 0. Right? It's exact. So the image of gamma is 0. So gamma is actually the 0 map. It's the 0 mapping. So it's the kernel of the 0 mapping. And the kernel of the 0 mapping, well, it's everything, right? So it's H1 of P2. So basically what we've shown is we've shown that the beta mapping, it's a surjective map. So this is a surjective map. So it remains to find this kernel. Now we can say that the kernel of beta, by exactness again, this is the image of alpha. Right? That's the image of alpha. But what is alpha? The image of alpha, it doubles everything. So it's just 2z. Right? 2z. So thus, z mod 2z, because that's what the kernel is isomorphic to the image, but we said it's surjective. So it's isomorphic to the first homology group of P2. And look at that. We've calculated the first homology group of P2. It's isomorphic to z mod 2. So that's the way you can get it. And I think it's a very interesting calculation because you're using a big part of the sequence. You're going 2 back and you're going 2 forward, and you're using all of those maps to help analyze what's going on to get this nice result in the end. Now, for those of you who are interested, there's going to be a homework problem where you're going to compute the homology groups of projective space, projective 3 space, and the homology groups of projective 4 space. And then from here, it will be clear how to generalize to Hn of projective M space. If you're interested, you can look up this result. That's a well-known result. It's an interesting answer. But on the homework, I'm just going to make you do it for 3 space and 4 space. This one is easier. This one is a bit harder. And the homework will give you a suggestion to how to do it. And it'll be essentially the same argument that we just did, but it's almost essentially the same argument that we just did. And then once you see how it works for 3 and 4, you will see how to generalize it to higher dimensions. It's almost like a proof by induction, except you do have to consider the even and odd cases a little bit separately. So that will be an interesting homework problem for you to think about. And then from there, you will know the homology of projective M space in general. For the last example, we're going to find the first homology group only, just to keep it more interesting, because this is going to be the most interesting one. The first homology group of X, where X is a orientable surface of genus 2. So if you're not sure what that means, all it means is that X looks like this. So that's your surface. It looks like 2 tori, but not quite, because they're being kind of put together like that. So here's the way we're going to do this. This is going to be U. Obviously, I mean intersected with X, so that's going to be the U portion. And then this is going to be the V portion. And we're going to calculate we want to find the first homology. So we're going to, as before, we have the reduction map, the reduction of degree, U intersect V. And the intersection of U and V, well, it's this sort of piece in between. You should be able to see it. It basically is just, it's basically just this. It's like a tube or something, right? It's just how they overlap. They overlap in a tube, because when you remove, when you like sort of cut that away, you have it hollow, so you have that tube. And then you have H0 of U plus H0 of V. Now, as a group, this one is isomorphic to the integers, and this one is going to be 2 copies of the integers. And just like we had with the projective plane, this is just the diagonal map. This is very easy to understand because this is H0, it's just half components. So this is clearly going to be an injective map. Now for the other ones, for the next one, this is going to be H1 of U plus H1 of V. And then we have H1 of U intersect V, like this. So we have all of these maps. And let's give these maps names. Let's call this one alpha. We call this one beta, gamma, delta, like that. Now, we do know that gamma is injective. So the kernel of gamma is 0, which means that the image of gamma has to also be 0 because of exactness. So this is 0. So this is just the 0 map. So if this is the 0 map, then what does that mean? Well, then it means that, well, that means the kernel of gamma is 0. I'm sorry, the kernel of gamma is everything. So it would mean that the image of beta also has to be everything because of exactness. So this map is therefore surjective. So you can see that by just knowing that this is injective, we're able to get all of that information. So that's how we're exploiting exactness. Now let's try to analyze what these are. Now H1 intersect U and V, it's the collar, right? It's a tube. This is homotopic to the circle, so its first homology group is isomorphic with Z. So that's fine. Now these two are kind of interesting. So this is so let's just look at U. So U is the following open set. You see that it's maybe what I should do over here to indicate that it's open. Maybe I should make it like with like a dotted line, like that. So sort of the open portion over here. So that's what this is. It's sort of like a torus, but it's been opened up somewhere over here. And basically what this is you can say this is a punctured torus. So if you take a torus and then you make like a little hole over here, then you can open up that hole, right? And then you get something like that. So that's a punctured torus. And this is like a well-known fact. Let's say this is a lemma. This is a well-known fact. It's used a lot in topology. So I'll write it down, and then we will explain why that is. So the punctured torus is homotopy equivalent to the figure 8 space. So let me justify this for you. It's a nice justification. So here's the visual. Again, you can make this rigorous, but that's what we call missing the point. You can convert those, every picture that you see here, you can convert it into a formal proof. So the easiest way to visualize this is to go back and think of the torus in a way where this side is being glued with that side, and this side is being glued with that side. And now we're going to introduce a puncture. So this is your hole. That's your puncture. When you introduce that puncture, you can then take that puncture and you can just sort of move everything out to the outside, right? You can just homotope everything from that puncture to the outside. So as you move everything to the outside, this hole, it kind of gets extended to the sides, and then you're just left with the shell. You just have the shell, the outside shell remaining. Like this. So this is just the outside shell that you have on the torus. And this outside shell, well, this is glued with that. So you can kind of not even draw it because that's just redundant. And this is redundant. So you get these two. But then you have to understand this is really a circle because this point and that point, they come together. So you're getting a circle and then you're getting another circle. Like that. And that's what you end up with. If you do not like that kind of a picture, another kind of picture you can do is, like another way you can see this as you go back to your torus, and you have the ring going like this, and then you have a ring going like that. And then if you introduce a puncture, you can sort of homotope it to the two rings, but I think that's harder to actually see. So you get two circles that meet at a point. I think the picture that I drew earlier makes it a little bit easier to see what's going on. So the punctured torus is homotopy equivalent to the figure 8 space, which we write as S1 wedge S1. It just means two circles that are joined at a single point. So that's the meaning of this. So when you're computing the homology of U by homotopy equivalence, you can just say that, yeah, the homology of U by homotopy equivalence, you can just say that it's the homology of the figure 8. So you have one of the circles going like that and one of the circles going like that. So, so that would mean that the homology of U is isomorphic to two copies of Z, right? Every circle gives you your own homology class, so you have two generators. So this one is going to be Z plus Z. And then the other one is also going to be Z plus Z for the exact same reason. If V is just another copy, almost identical copy of U just on the other side. And now I'm going to tell you something that is going to be very interesting. This map alpha is actually the zero map. So yeah, you're mapping the integers into z to the 4, right? This is z to the 4. So you can ask, what is this map actually doing? What is this alpha doing? So it turns out this is the zero map. As surprising as that may be, that is actually the zero map. I will explain to you in a moment why that's the zero map. But if we're willing to accept that this is the zero map, we can now calculate the homology by looking at this. So if you look at this morphism, then by the fundamental isomorphism theorem, you're going to say that the image of beta is going to be isomorphic to this group, which is z to the 4, mod the kernel of beta. But the kernel of beta is the image of alpha. But alpha is the zero map. So this is z to the 4 mod 0. So this is just z to the 4. And we have shown that, now the image of beta is of course h1 because it's a surjective map. So we have shown that the first homology group of such a surface is isomorphic to z to the 4. Okay, so this is like another interesting example where you're using Meyer-Vietoris sequence. But the question, of course, that's going to come up is, why is this the zero map? And this is the part that makes this very interesting, very, very interesting. So let me actually remove all of this stuff on board because we do not need it anymore. We've done our calculation. So it just remains to justify why this is the zero map. So here's what it has to do with. Now, what is U intersect V? U intersect V, okay, let's do it like this. How about we remove everything? So this is just getting in the way. So let's start from the very, very beginning. We're going from H1 U intersect V into H1 of U plus H1 of V, like this. So we're taking a class and we're mapping that class diagonally, like this. So this is the homology class in U, and this is the homology class in V. Now, recall what I said earlier, that this might look like an injective map, but it could happen that these become zero. And in fact, what's going to happen in our calculation here is that these will end up being zero, and that's why you end up getting the zero map. But how do we justify that? Well, here's how we justify this. So let's just justify this one, because the second component is going to be almost the exact same proof. So let's just justify this one. So let's draw the picture of U again. So U, it looks like this. That's the way U looks like. What is U intersect V? U intersect V is that collar that we're getting. So basically this collar, you can see it like right over here. That's the collar. Now, we've said that the first homology group of this collar, it's isomorphic to Z. So because it's isomorphic to Z, you have a generating cycle, right? One generating cycle. And the generating cycle is the one that goes one time around, right? Because this collar, it homotopes to the middle circle. It homotopes to this middle circle, like this. And so the generator for that group would just be the cycle that goes around it. So you have this cycle, right? This is the cycle that generates the group. And so this is the cycle drawn in this space. But that cycle is also a cycle, you can draw it over here in this larger space U. So here it is. So this is the cycle drawn. So this is C. Okay? And what we're claiming here is something that's quite amazing. So we are claiming, and you're not going to believe this, but we are claiming that C as a one cycle in U is actually homologically trivial, which seems impossible, right? That just completely seems impossible, because you're like, I mean, you look at this and you're like, but how do you collapse it to a point? So this example nicely illustrates actually illustrates the difference between homotopy versus homology. So this cycle, C, is homologically trivial, but not homotopically, but does not homotope, but not homotopically trivial. That something being homotopically trivial is a stronger condition than being homologically trivial. Actually, if you think back to the Horevich isomorphism, we've actually made that observation. We saw that if two one-cycles can be homotoped, then they are homologically trivial. This is what made the Horevich homomorphism a well-defined homomorphism, because two things being homotopically the same is a stronger condition than being homologically the same. So I'm claiming that C becomes trivial. Now, this is a little bit surprising, but let's actually draw. We're going to draw some pictures, but let's talk about the homology group of U. So the homology group of U, we know that one is isomorphic to Z plus Z. So that means we have two generator loops. And in our picture, it would go like this. So this is U again. So one of the generator loops, it's going to go around this inner ring. And the other generator loop is going to go around this one. Well, I mean, it doesn't matter how you really orient it. It's going to go around this one. And we're claiming that this C that we're getting, well, it's clear you cannot really homotope it into that one, but we're claiming that the C, you see, this C is not, it's not this one and it's not that one. And we're claiming it's trivial homologically. So how can you justify this? Well, here's how you can justify this. We're going to go back to our picture of the torus again. So this is the way we like to think of the torus, that one of these sides, like these two sides get glued together, and when you glue them together, you get this one, and the other two sides, when you glue them together, you get that one. So that's how you end up getting the torus. But we have a punctured torus, right? Keep in mind, this is a punctured torus. So because it's a punctured torus, this hole over here that we have to stay away. So you can kind of maybe make a little, so this is sort of like the puncture, right? That's like that hole, like this. And what's going on? Well, this C that we're drawing, it's the one that's going around that hole. So let's draw it around that hole and see what happens. So here's the C when we draw it around the hole. And now here's the question. So to show that C is homologically trivial in the punctured torus, we need to show that C is a boundary of a two chain. So can you find the two chain, right? Something is homologically trivial if it is the boundary of something. And the answer is yes. Here is what is, you can actually, maybe you can already see what it is. I'll shade it in for you. There it is. This is a two chain because it can be broken up as a formal sum of two simplices, right? You can triangulate this using two simplices. So this is a two chain, and the boundary that you're getting for that two chain is exactly C. So you can get C as that. If you do not like that argument, I have another argument for you that's kind of interesting. So here's what you can do. You can slightly deform C so it goes like a square. Okay, so that it goes like a square. And let's give it an orientation. So it goes like this. And now take this square and start pushing it outside to the boundary. So start pushing it further out. Start expanding that square. So you're basically homotoping that picture, but you're not really changing the homology as you do. So as you push it out. So as you continue to push it out, notice that you're aligning yourself with this, right, with the one that goes around, like with this cycle. you're aligning yourself with that cycle. But when you get to the, you see the arrow now goes backwards. So you're kind of going in the opposite orientation. So what you really are seeing is that the homology class of C, it's homologically equivalent to A. So you call this one, maybe you call this one A, like this. So this is A. Then you go around the red one. You go around the red one, so that's plus B. But then you go A, B, and then here you're going opposite. You see, you're kind of going the opposite direction. So that's really negative A. And this is going in the opposite direction. This is negative B. For those of you who have seen how you use the Seifert-von Kampen theorem to compute the fundamental group of the torus, this will actually feel very reminiscent of that. But the big difference is this is all commutative. And in the end, what are you getting? A minus A, B minus B. And so you end up getting just a homology class of 0. So we have shown that the homology class of C is actually trivial, which is something that's really surprising. Like if you look at this picture, you would not actually say that C is the boundary of a 2-simplex, but it is. It is. And in fact, here's perhaps the easiest way to see this. I mean, if you do not like those pictures, you can make the picture even simpler, right? You can make the picture even simpler. Just do this. So just do this. Just draw. Okay, maybe I'll try doing this one more time. Just take the part where C stops, right? This is exactly where C stops. And this piece that you're getting, this is a 2-chain. That's a 2-chain. This whole thing is a 2-chain, right? I mean, basically, intuitively, a 2-chain is like a surface or something. So that's a 2-chain. And the boundary of this 2-chain is exactly C. So C is a boundary. And so because it's a boundary, it's homologically trivial, which is really surprising. You would not think this is homologically trivial, but it is. And so this mapping maps this to 0, and for the same reason, it maps this one to 0 as well. And so you have shown that it's the 0 mapping, okay? And that was like the questionable step in that calculation. So now we have shown something quite nice, right? So we have shown that the homology group of this orientable surface of genus 2 is isomorphic to Z to the 4. So that's fairly interesting, and you can see how it follows from the Meyer-Vietoris sequence.